And in this lecture, we'll be talking about a state space approach. And one of these techniques will be the signal flow graph, something I believe most of you are familiar with. Okay, so the outline for this lecture, we'll talk about the general definition of state space approach. Usually, state space approach is usually algebra. And we'll talk to about the signal flow graph and how to represent the transfer function using the Mason-Gain formula. And we'll see the state space representation like convert between here and there. So the state space representation, you have it like in the form of matrices. And we'll see how it's going to convert it to signal flow graph. And also the conversion from block diagram to signal flow graph. Basically, the block diagram, we have the elements of adder. You have like the feedback block, forward block, and let's say a junction or node. And that's the last topic, the Mason-Gain formula for the transfer function. So the state space representation of a system is, let's say, our internal and detailed description of the system. And given, let's say, as I mentioned, that's linear algebra and matrix equations. So basically, I have my, let's say, the expression will be, let's say that's y equal a certain combination of a matrix A with a vector X. That's the vector of inputs. So it does provide insights to the system behavior. Something we've done in the control systems, something we call controllability, that if you want to modify some properties in the system, and you can check if the system is controllable, you can have some insights on the behavior. It allows a unified handling of systems with multiple inputs and multiple outputs. In the end, you will have a linear system with matrices, so it doesn't matter how many inputs or how many outputs you have. Like you have a unified way of solving these systems. It is extendable to nonlinear and time-varying systems. It is a general format. It, let's say, works for linear and nonlinear time invariant. So basically, all kinds of systems are represented using the state space representation. And usually the analysis is based on the initial condition. However, we usually consider the initial condition to be, let's say, 0 at t equal t naught. Like that's the initial time. All right. So the state space variables can be represented as memory elements. So we have the unit delay element is represented mathematically by an integrator. And the amplifier is just a gain. And the adder, you have the addition like that. So that's the discrete memory elements, and you have the continuous memory elements. So in both cases, the output of the memory elements can be selected to be the state variables of the system. All right, so the signal flow graph, we have it, everything represented in nodes and branches. So this is what we call a branch. It's just an arrow pointing to a certain direction. And a node is just a connection of branches. That is what the node is. And this is the branch. Okay, so the signal flow graph is another graphical representation of algebraic equations such as the transfer function. So its basic elements has only nodes and branches. As I mentioned, node is just the combination of branches. So node is a point which represents either a variable or a signal. There are three types of nodes. You have an input node, output node, and the mixed node. So here, this one is the mixed node. Input node, that's your input, and that's your output. So that's input node, and that's the output node. And you may have whatever combinations of signal flows graph like branches here. So this one here will be considered as a node, similar here, etc. So branch is a line segment which joins two nodes. It has both gain and direction. So here the branch has a direction, and the gain could be 1, 3 over z, or 3z negative 1, etc. So here is an example here. So if we look at this signal flow diagram, and if you're asked how many branches, how many nodes are there? So regarding branches, you have the first branch, second, third, and fourth. So we have 4 branches. Easiest way to find branches, look for the arrows because it has the direction and the gain. So the gain here is A, B, C, and the gain is -D. Now, regarding the nodes, you have the first node, that's the input node, and you have the output node, and you have these 2 mixed nodes here. Now, when you have a node with 2 arrows going inside of it, that's going to be an adder node or addition node, and the output will be the result of their summation. So in this case, it's going to be A minus D. That's an example here. Here, like this node is coming in, but there are 2 nodes coming out. That's also a mixed node, but there is no addition here. So just like a joint node, like joining several lines or several branches. So the nodes represent in this graph are given, and you have input node and output node, and you have mixed nodes. The 4 branches, as I mentioned before, with these gains. So the advantages of signal flow graph, it's easy to understand. Instead of having multiple blocks with a lot of elements, here there are only 2 elements, the branches and nodes. You have the ability to represent multiple inputs and outputs in a compact way, making it ideal for complicated systems. It is easier to be, let's say, written in step-by-step procedure and contain less elements compared to block diagrams. And also, we'll find it later now, to find the gain for the whole system, or represent like this whole system by a single block or single branch. So drawing the signal flow graph. So the steps: draw all the nodes starting from the input node all the way to the last node. Start with the first equation and start drawing the branches. Continue as required and combine into one graph. So if you look here, so you have, actually that's not a complete system, but if you look here, that this is one node, 2, 3, 4, 5, and here there is Y1. So how many nodes we have? 6 nodes. So it says that draw all the nodes together. Okay, so that's 6 nodes here. So let's assume this is Y1, Y2, Y3, Y4. This is just an example for illustration. Y6. And if you look at the formulas or the expressions here, you have only Y1, that's independent variable or independent, let's say, node, and all others rely on expressions. Let's say Y2 relies on this expression. Y3, similar thing here. Y4 here, for example, it relies on this expression. So here we can conclude that Y1 is the input node. And the last one will be the output node. All right, so let's start step by step. So you have Y2 equal A12 Y1. So you have a branch here, or the arrow should be here, A12. That's the first branch. Second branch is coming from Y4. Y4, you can draw it up or down, doesn't matter. And that's the direction, and that's going to be A42. That's the gain for this branch. So that's it. You can take the first formula. We just finished that, the branches coming out of this. Now, Y3 equal A23 Y2. So you have Y2 here. That's A23 plus Y5 AY3. So like this. A53. Now Y4 equal A34 Y3. So that's Y4 here. A34. All right, now Y5 equal A45 Y4. So that's Y4 here. That's A45. It's just a step-by-step procedure. Now you have a branch coming from Y3. So Y3, you can just write it this way. That's A35. And Y6 That's the branch there, A56. And that's it. That's the signal flow graph for this system given to you. So the most important part is to identify the nodes, and then you can do the expressions one by one. Where? Which equation? This one? This one? Y2 is this one, and coming from Y4 is the opposite, yeah. Yeah, the plus. No. So you're talking about the gain here is going to be positive or negative? No. So A42 is a constant. It could be negative, could be positive. So yeah, don't usually, let's say, think, oh, if the arrow is going there, so that's -3. No, it doesn't have to do, because it depends on the adder itself. If the input of the adder, like this, that's a positive and that's a negative, and the block diagram was 3, then yes, I will put a -3 like this. It depends on the adder. So in this case, we are under the assumption are all adder with 2 positive inputs. All right, so here are the steps. We've done them. So it's pretty straightforward. Again, location of the branches upward or downward is not an issue. Now, how to convert the block diagram into signal flow graph, represent all signals, variable summing points, and take. Now we are talking about what you just said. Now, if we have a summing point with a positive input and a negative input, how will that be reflected in a signal flow graph? So represent all signals, variable summing points, take off points or pick off points, block diagram as nodes in signal flow graph, represent the blocks of block diagram as branches in signal flow graph. So let's summarize everything. Let's say when we do the steps, pretty straightforward. We want to represent the transfer function into signal flow graph by substituting all these elements into branches and nodes. So basically the block will be a branch, summing points, like here, summing points, takeoff points will be nodes, variables, blocks will be branches. All right, so this block diagram here, if you think about it, it looks complicated actually. Like there are a lot of summing points, a lot of elements, a lot of nodes, etc. So how to convert this block diagram into a signal flow graph? Pretty straightforward. We'll do the same procedure. We'll have the input nodes and output nodes and all the nodes between, and we'll do the branches based on the block diagram. So let me take this one into the whiteboard. Just double check if the mic is working. Okay. All right, it's working perfect. All right. So a new whiteboard. Okay, so if you look at the nodes here, we have plenty. Let's start from RS. That's my input node. And there is Y1, Y2, Y3, 4, 5, 6, 7, 8, 9. And here is the output YS. So that's RS. And here is YS. Okay, so RS, it goes to Y1. So there you go, that's one branch, and the gain will be 1. That's it. Now we have a summing point. The summing point is represented by this node, which is Y1. That's node Y1. Now it has 2 inputs. The first input is coming from RS. The gain is 1. Now the other input is coming from Y8. So 1, 2, 3, 4, 5, 6, 7, 8, 9, and here's the Y. So Y8, there is a long branch that has, so something like this. The gain is H2. Now what will be the sign of H2? We'll go and look at the summing point. So I have positive and positive. So that's addition. So there'll be no change in sign here. because this is going to be the output here will be RS plus H2Y8. So that's Y8. And here's H2. So there's no change in sign. Now, let's look at the other node here. Now, is there any elements here? So the gain will be 1. So going from Y1 to Y2, there is nothing, no blocks. So the gain will be 1. So this branch has a gain of 1. Now, Y2 has two inputs. The one's coming from Y1, which is with the unity gain. The other one's coming from Y4. Y4, you can draw it this way. So signal going backwards, that's the sign. Now the gain is H1. Now what will be the sign of the gain? We have a negative sign, so that's going to be negative H1. Is it clear? Okay, so let's have a little bit of space. All right, so we are done with Y2. Now it will go to G1 and G2. So from 2 to 3, I have this branch, G1, and from 3 to 4, there is another branch, G2. Now, someone might say they are in series, I can just multiply them. Yeah, you can do that, but let's stick with the reference we are given. All right, now the output of Y4 will go to node Y5. So again, there is nothing. So the branch again is 1. Now Y5 is a summing point. We have an input coming from Y9 all the way to Y5. So that's Y9. And you can do it this way. That's Y5. And what will be the gain? H3, the sign is negative also because the input here is negative. Y5 will go to Y6. Unity gain. Now Y6 will go to Y7 through two paths, G3 and G4. So the first one immediately, that's G3. And here also another path, that's G4. And is there any change in sign? No, just addition. And the output of Y7 will go to Y8. Gain is 1. Now the output of Y8 will go to Y9 with again G5. And the last Y9, which is the same as YS, it has a gain of 1. And that's it. If you want to compare this to the answer provided there, they kind of look similar. It's just they draw it in a way that the branches do not intersect. Mine has, let's say, this intersection here, but that's still fine. Or I can draw this branch. Okay. This branch, I could have drawn it all the way from the bottom. All right, so this is it. This is how you draw from, or you go from block diagram into a signal flow graph. Okay, the gain, if you go say here, if it's not, there is no block, it has to be 1. But if there is a block, that's the gain. The gain given to you is G1, G2, etc. But like this transition from Y1 to Y2. So here is node Y1 and here's the node Y2. And there is, let's call it a wire between them. So just connect it together. So that's a branch. The branch should have a direction and gain. So we gave it the direction. What will be the gain? It's the same values. Like I'm putting Y1 as the input to Y2. So it's as having here saying that Y1 times 1 will go to Y2. So you put the unity gain. So usually when you have a branch that you don't know, that has no gain here, like explicit gain like this, you just give it the value of 1. And that's why you have a lot of ones here. And let me see if we have the same thing in the slides. Yeah, we have a lot of ones there. Clear? Did I answer the question? All right. All right, now the state space representation. A system like this, I want to represent it in a signal flow graph. First of all, this one could be easily represented in matrices. Like, for example, you have this one is x1 naught. And there you go, that's x2 naught. Now, x naught in control theory and state space representations in general, that's equivalent to x prime or dx over dt. So x naught is basically the derivative. So this system here is represented in a matrix representation. We have x1 prime equal negative 6x1 minus 2x2 plus u of n. And you have x2 of n prime equal 2x1 minus x2, and you have y equal 3x plus 3x1 plus 2x2. Now, from this one, we can represent it into state space representation by two expressions. Now, with the state space representation, we will be dealing with matrices. Basically, these formulas with x1 prime, x2 prime, you can create a system out of them. And with y, you have another system out of that. Now, these systems are combinations of x's, like of the inputs, x and of the state variables x1 and x2, and you have the input is usually the unit step function u of n, and the output is y of n. So in both expressions here, x1 and x2 prime will be like this, represented as some matrix multiplied by x1, x2 plus some vector multiplied by u. That's the first expression you are getting out of those. Second one, y will equal a vector multiplied by x1, x2 plus similar thing, a scalar u of n. Now the task is to find these matrices or vectors from this state space representation. Best way to do it is to do aligning. You align x1 and x2 together, and the matrix will be built immediately by looking at x1 and x2. So if I want to take this expression or this formula, the whiteboard, okay, copy. Now I have the formulas like this, so I will just rearrange the writing. So x1 prime equal negative 6x1 of n minus 2x2 of n plus u of n. And x2 prime equal 2x1 minus x2 of n plus 0 u of n. And so that's it for these two formulas or two expressions. And y equal 3x1 plus 2x2. Now the target is to write x1 equal some matrix, let's call it ax plus bu. And similarly for y equal cx plus bu. Okay. Now if you look at the matrix A, since we have two inputs, so this matrix will be 2 by 2. And this vector is going to be 2 by 1. And this one is going to be 1 by 2. And this is going to be 1 by 1. Something like that. Now, if you look at the matrix A, just look at the coefficients. They are already organized. So I have negative 6, negative 2, 2, and negative 1. That's A, already organized. What about B? Uppercase, lowercase, doesn't matter. By the way, this is D, sorry. D. B, we said it's going to be a column vector, and you can see it here. There is no value here, so that's a 1, and we have 0. So that's 1 and 0. What about C? That's the thing associated to Y. Look, here's already organized 3 and 2. And D, since there is nothing for U of n, that's 0 U of n. That's a 0. So that's the state space representation of this differential system that was provided. All right, so -6, -2, 2, and -1. Similar values here. And we have 1, 0 here, 3, 2, and 0. Now, if you want to confirm your solution, just x is basically a vector, x1 prime, x2 prime. And x is another vector, x1, x2. And here you just U of n. There's no, it's not a matrix, it's not a vector. Similar thing here. We have y, just y, there's no y1 or y2. And you have it similar to x1, x2. Now distribute -6 by x1 plus -2 by x2 plus 1 by u. So that's the first expression here. So, or basically you want to write the full system. So it's going to be x1 prime, x2 prime equal -6, -2, 2, -1, x1, x2 plus 1, 0 u. Okay, now solve this matrix. So x1 prime equal, basically I'm going to consider the first row here for this matrix. So it's going to be -6 x1 minus 2 x2 plus 1 u. So I consider the first row in these matrices. Now x2 prime equal 2x1 minus x2 plus 0 u. And that's going to be exactly the same that was given before. For y is pretty straightforward. Y will equal, I have 3, 2, x1, x2 plus u. So distribute, y will equal 3x1 plus 2x2 plus 0 u. And that what was provided before. All right. All right, so let's look at some basic diagrams here. We're dealing with Laplace also. So even though in DSP we're usually dealing with the Z transform. Show from current slide. Something we have seen in signals assistance. And by the way, you don't have to worry about what they call it, the transforms. We're not going to use any transformation here. Just you have the expression, you have delta will equal to 1 u 1 over s, etc. It's just showing you that most of the elements will be either a delay unit by applying a unit step function or an integrator. Integrator is this one. Okay, so that's the signal flow graph here. That's an example, but in the Laplace domain, you have the input node u and the output node y. And let's see how many branches do we have. So that's 1, 2, 3, 4, plenty, a lot of branches. How many nodes? 1, 2, 3, 4, 5, and 6 branches. All right, so that's the signal flow graph, and the task will be given this whole thing represented into u, and you have only one branch, and you have y. And this is going to be the T of S. So this whole thing like the block diagram reduction. You did not do control theory, but that's in the control theory, that you have a complicated systems like this, and in the end you want to have a single block represented. That have you taken control? You okay? So this thing should be familiar with you. All right. So yeah, from this signal flow graph, I want to find a single branch that represents this whole branches here. And for this one, we'll use something called Mason's gain formula. So the Mason's gain formula is just an expression that you have to apply certain, let's say, extract information from the signal flow graph given to you. And from this information, apply the formula, and you will immediately have the output expression ready there. All right, so the Mason's gain formula is used to solve for the transfer function when you are given the signal flow graph. It is based on the following equation or expression. So that's the transfer function equals the output over the input. And you have the summation over the number of straight paths, 1 to n, pi delta I over delta. Now the task is to find p, delta, and delta I and pi. And I will be going from 1 to all the way to n. N will be the number of straight paths. What's meaning of number of straight paths is basically how many ways I can go from U to Y without any feedback, like going straight forward. The easiest path is this one, the straightforward path. That's one path. Now you see this one is a feedback, that's not a path. Also this one is a feedback. However, if you look at this one here, so you can have this path also. That's the second path. Now, are there any other? No. So here, n in this case will be 2. So I need to find path 1, path 2. And for each path, there will be delta 1, delta 2. Okay. All right. So that's the first thing, to identify the number of straight paths. And the other thing, you need to find the loops. Like in this one, how many loops are there? Like this is the first loop, second loop, and this one here, that's the third loop. This one is not a loop. This is a straight path going from there to there. So we have 3 loops. Now let's call each loop L1, L2, L3. So you need to identify these variables first. P1 and P2, immediately you can find them. Also L1, L2, L3, immediately you can find them. Now the work will be is to identify deltas. Now these deltas can be identified by having this larger delta, let's say. This delta that does not have an index. And there is an expression to find this delta. All right. So this is the formula, same information from before. Now this is delta. It's going to be equal 1 minus the summation of all individual loop gains. So in the previously, I have L1, L2, L3, summation. Plus sum of gain products of all possible 2 non-touching loops. Like you have loops that are non-touching, which means that there is no common branch between them. So let's assume this is loop number 1, loop number 2, and this is loop number 3. If you look between loop 1 and loop 2, are they touching? No. So L1, L2, non-touching. What about L1 and L3? So this is L1 and this is L3. Notice that there's this common branch between them, so they are touching. L2 and L3, there is also this common branch that is touching. So these are all 3 combinations of these 3 loops, either L1 and L2, L1 and L3, and L2 and L3. So L2 and L3, they are touching. L1 and L3, they are touching. L1 and L2, they are not touching. So in here, you will go back to the expression, sum of gain products of all possible 2 non-touching loops. So the products of L1 and L2. And that's it. This one we usually reach to this level. This is again for the specific problem that was given to us. Some signal flow graphs may have L1 and L3 probably not touching, and so on. So this is problem specific. All right. So for this particular example, let's solve it. Discard. I'll take this one. All right. So the expression is as follows: T, or the transfer function, equal summation of Pi delta I over big delta. And we said I equal 1 to n. Now, n in this case, we agree that's the number of straight paths. So it's going to be 2. So then in this case, my summation will become P1 delta 1 plus P2 delta 2 over delta. All right, now P1, the first path, equals what? This whole straight path here. So this one says there is a number, that's a 1. Now 1 times 1 over s, so it's going to be 1 times 1 over s times 2 times 1 over s times 2. And that's going to be equal to 4 over s squared. Second path. Second path, we said is going to be this one here. So 1 times 1 over s times 3. That's going to be 6 over s. That's the second path. Now, before identifying delta 1 and delta 2, we need to find the loops. So first loop, second loop, and third loop. So let's assume this is L1, this is L2, and this is L3. So the gain of the loops is just multiply these branches in this circle. So I have 1 over s times negative 6. So it's going to be negative 6 times 1 over s, negative 6 over s. That's the first loop. Second loop, I have 1 over s and negative 1. So negative 1 times 1 over s. So negative 1 over s. Third loop, we have these branches. So I have 1 over s times 2 times 1 over s times negative 2. Negative 4 over s squared. So we find the loops. Now let's find the big delta. Equal 1 minus the summation of all individual loops, L1, L2, L3, plus summation, plus the product of the non-touching loops. Now let's look at the non-touching loops. L1 and L2, they are not touching. So L1 times L2. We saw that L1 and L3, they are touching through this branch, and L2 and L3 also touching through this branch, and that's it. Now let's substitute the values. 1 minus L1, negative 6 over s, negative 1 over s, negative 4 over s squared. So this is are all the loops. Let me just double check. They're all negative. Okay. Plus L1 times L2, negative 6 over s times negative 1 over s. And in this case, let's simplify. 1 minus, so square s square s to unify the denominator. They will be all added. So it's going to be negative 7s minus 4 over s squared plus negative positive 6 over s squared. Okay, so in this one, s squared. So I will have 1 minus 7s. Sorry, 1 minus, that's going to be positive, plus 4 plus 6 over s squared. So in this case, it will become, we have s squared here, sorry, from this. So s squared plus 7s plus 10 over s squared. So that's delta. Let's double check the answer should be there. S squared plus 7s plus 10 over delta. All right. So we have the delta. Now the task then is to find delta 1 and delta 2. If we go back to the slides, each individual delta is obtained from delta by removing the loops which are touching the ith forward path. So we'll go back to the big delta here. So that's the big delta. Now I need to remove delta 1, remove the loops touching P1. So it says here, delta I is obtained from delta by removing the loops which are touching the ith path. So delta 1, remove the loops that are touching P1. All right, so let's look at P1. And we notice what? So this is P1. So L1 is touching that, L2 is touching it, L3 is touching it. So all of them are touching it. So I need to remove them all. So in this case, delta 1 equals 1 because I removed all the loops. Now about delta 2. Now I need to remove the loops that are touching P2. Now this is P2. Now we notice that L1 is sharing this branch with P2. So remove L1. Also, if you look at this loop 3, it's the same branch. So this is the branch for the path, and this is also the branch of the loop. So L3 will be gone. What about L2? So this is the straight path, and L2 is in the middle, so it does not touch it. So L2 remains. So we'll go to the expression. We will have just 1 minus L2. Because L1 will be 0, this will be gone. L1 and L3 will be removed, also will be gone. And in this case, it's going to be 1 minus L2 negative 1 over S. Negative 1 over S. So it's going to be 1 plus 1 over S. S plus 1 over S. So we found delta 1 and delta 2. Now we can find a transfer function. P1, how much was it? Is the first thing here. So 4 over S squared. Times delta 1, 1 plus P2, 6 over S times S plus 1 over S. This whole thing over S squared plus 7S plus 10 over S squared. Now let's simplify this term. So we will have 4 over S squared plus, so just multiply 6 times S, so that's 6S plus 6 over S squared since the denominator is unified over S squared. So I'll have 4 plus 6S plus 6 over S squared over S squared plus 7S plus 10 over S squared, so square here. And simply these two will be gone, and the final answer will be 6S plus 10 over S squared plus 7S plus 10. And that's the final answer. So let's double check with the slides. Okay, so we got that right. Delta 1 is 1, delta 2 is s plus 1. And okay, so we calculated delta. The paths are fine. I have 3 over s. Did I put it right? 3 over s. 6 over s, I have it there. Why? Okay, I included this one by mistake. This 2. The path is like that. 1 plus 1 over s plus 3. So that's 3 over s. Oh, yeah, 3. Why did I have 6 here? So that's 3 here. Okay, it will not change a lot actually. So it's only here I have 3. So it's going to be 3s plus 2. Yes, plus 3, sorry. Yes, 3s plus 3. Then we'll have 3s plus 7. Okay. Okay. And there we go. 3s plus 7 over s squared. This is a mistake. 1, and there's no s. Because there should be an s squared here. So they will cancel each out from there. All right. So there's a small typo here, but the correct solution is there. 3s plus 7 over s squared plus 7s plus 10. That loop. Sorry, forward path P2. Okay, let me remove everything by the eraser. So the second path is like this. So I have 1 times 1 over s. It doesn't see the 2. Times 3. 1 times 1 times 3. So I have the expression correct. Just I wrote the wrong answer. So 3 over s. And everything is pretty straightforward. And it is the same. I'm not sure if this lecture has a worksheet actually. It's lecture 7. So let's go to the tutorials. There is a tutorial. All right. All right. Consider the following system. To write the state space matrix representation, draw the signal flow graph. Using the signal flow graph, use Mason's gain formula to calculate the transfer function, and so on and so on. So calculate the straight path and closed loop path. Calculate delta as well individual deltas using the Mason's gain formula. So let me take a screenshot of this. Copy. Okay. By the way, the requirements, they are independent from each other. So A is not related to B. So if you don't solve A, doesn't mean that you cannot solve B. So this one is pretty straightforward. Let's represent it into state space representation. So let's see what we have here. Okay, let's write them aligned. X1 prime equal negative 2x1 plus 4x2 plus u, and x2 prime equal x1 plus 2x2 plus 0u, and y equal 3x2 plus 0x1. All right, so in this case, x1 prime, x2 prime equal negative 2, 4, 1 and 2, x1, x2 plus 1, 0, u, and y equals 0, 3, x1, x2 plus 0 u. And that's it. So that's the first part. Now the signal flow graph for this system. So we've done block diagram signal flow graph, but we have this linear system. So we need to identify, like in the previous, what we did there at the beginning, the steps. So draw all nodes, starting from the input node and finish at the output node. So we'll go here. What is the input node and what is the output node? If you think about it, input node is usually U and the output is Y. So I'll start by having U of N. That's my input node here. And decide somewhere far, that's the output Y of N or Y. Now, what are the nodes in between? These x1 prime, x1, x2, x2 prime. Now, there is no specific order for them actually, but it's better to have it like in the sequence. So x1 prime is the result of x1, x2, okay. How to go from a derivative to the actual function? Let's say if I have my input x1 prime and I want to have a certain block unknown into x1, what will be this block? Integration. Now the integration, what is the process in here in Laplace domain that will grant me integration? The last part. So integration in time domain is represented by what? Multiplying or dividing over s, or multiplying by over 1 over s. So basically, if I have my input x prime here, and I want to add a certain block here to get x1, I will use 1 over s. So x prime, 1 prime, multiplied by 1 over s, I'll get x1. So in here, it's better to have the representation like this. I will have x1 prime, and I'll have right next to it x1. And in here, I will have x2 prime, and I will have x2. And the simplest block will be 1 over s, or let me write it in a better way, 1 over s, and x2 prime to x2, 1 over s. Clear? So that's it. Let's say identify the key elements here. Now let's write the signal flow graph. x1 prime equals how much? Negative 2x1. Here's my x1. Negative 2. Plus 4x2. That's x2. 4. Plus u of n. Okay. Clear? So we are done with the first expression. Second expression, x2 prime equal x1 of n. That's x1 plus 2x2. That's x2, 2. Y equal 3x2. That's it. Now, using this signal flow graph, find the Mason's gain formula to calculate the transfer function in the Laplace domain. How many forward paths are there? Just one. So in this case, T will be P1 delta 1 over delta. P1 is how much? 1 times 1 over s times, this is 1 over s times 1 times 1. So it's going to be 1 over s squared. P3, there's a 3 times 3. So I have 3 over s squared. That's P1. Now, how many loops are there? 3 loops, L1, L2, L3. First loop, -2 over S. So let's consider loop number 1, loop number 2, loop number 3. Loop number 2, 2 over S, and loop number 3, okay, so it's going to be 4 over S squared. So we have 4 over S, 1 over S, 1 over S. So 4 over S squared. All right, so let's find the big delta. 1 minus summation of L1 plus L2 plus L3 minus product of non-touching loops. So 1 and 3 they are touching, 2 and 3 they are touching, 1 and 2. L1, L2. Let's do the math. 1 minus L1 -2 over S plus 2 over S. Oh, interesting. Plus 4 over S squared minus L1, L2. So, sorry, this one is going to be plus. All right, -4 over S squared. Okay, so these two will cancel each other. 1 minus 4 over S squared minus 4 over S squared. So we 1 minus 8 over S squared. S squared is going to be S squared minus 8 over S squared. I believe there's a solution. Let's double check. Okay, right, like the way we drew it. There you go, S squared minus 8 over S squared. So far we are on the right track. All right, now we need to find delta 1. So that's delta. Delta 1 is how much? Is 1 minus, or remove from delta, remove all loops that are touching P1. And they are all touching it. So it's going to be 1. Because L1 touching this path, L2 is touching, L3 is touching. So all these L's will be gone, so you'll have 1 only. Now we are ready to do the substitution. So we have P1, 3 over S squared times 1 over S squared minus 8 over S squared. 3 over S squared minus 8. And that's it. Let's double check. 3 over S squared minus 8. Second question. Consider the following set of equations. Solve with yourself. Okay, work on it. Give it a try. This one, there is no x2 actually. It's straightforward. So you have only u, x1 prime, x1, and y. And no need to do the state space representation. You want to do it at home? I'm fine. Fine. Okay. You're done with classes today? Let's do it at home. All right. The solution is provided, so I'll give it to you. But try to work it on your own, then do it later. Okay. It is the same. Still in Laplace, so it's still the same. Stop sharing. Record and stop recording. Stop.